Hi, welcome to this video on gas laws. In this video, we're going to talk about a lot of our experimental laws. So we're going to start out with Boyle's law. So Boyle's law is one of our, I think, most famous, like the biggest known experimental law because it's one that's very easy to see. We see it happen all the time around us. Boyle's law, or Boyle, was actually known as the father of chemistry. Robert Boyle, and basically his law was that the volume of a confined gas is inversely proportional to the pressure exerted on the gas. So one thing to know is all gases are going to behave like this. And so we're going to get a little more into this. So Robert Boyle was an Irish chemist, and he was studying specifically, when he was studying, was the pressure-volume relationships in gases. So he was looking at how pressure and volume were affected. So remember, when you do an experiment, you can only change one variable, and then you look for the response that that one variable or that one change had. So you've got your one independent variable and your one dependent variable. So you only study two variables at a time, and you hold everything else constant to ensure that you get an experiment that isn't tainted by other variables or other things that could be possibly happening. So Robert Boyle spent a lot of time studying pressure and volume relationships. So that means that he was really keeping the quantity of gas the same, which would mean that at constant quantity, he had to have a closed container, and he was keeping temperature constant. So he wanted the kinetic energy of the gas molecules to remain the same, because we know that you increase your temperature, you heat them up, you speed them up, they're going to end up colliding with the container more, that kind of scenario. We've talked about that previously. So when Robert Boyle was studying just pressure and volume, he found that they had an inversely proportional relationship. That means that when volume goes up, the pressure is going down. So notice, in order for volume to change, your container must be variable. So when we're in lab, so the container must be able to, I don't know what I just did there, but somehow I can't write above that, must be variable volume. That's important. So basically, when we're in lab, if we were studying this, the variable volume container we would be able to use would be like a balloon, right? But it has to just basically be something that could change overall size. And so you can see down here in the picture in this molecular view, they're using something where as the pressure goes up or down, we can see that the overall size or that bar is moving. But basically what he saw was that for a given quantity of gas at constant temperature, the product of pressure and volume is always going to be constant. And so from there, he came up with what we call Boyle's law. So that is Boyle's law, which was what is in italics. But the P1V1 equals P2V2 equation is the easiest form of Boyle's law that we know that allows us to do calculations. So for example, we can change the conditions. We can start with a known set of conditions and of pressure and volume, and we can change the pressure of it and find out what the new volume should be, or vice versa. So it allows us to predict what the gas is going to do based on our known knowledge of the gas. So Boyle's law has been tested for over 3 centuries, and it holds true at low pressures. So keep in mind, if your pressure gets too high, then you have the problem of the possibility of condensing of the gases. So you wouldn't be able to check that or use that at higher pressures, at really high pressures. Most of the time, gas molecules are going to be at low pressure anyways. All right, so over here on the right, we can see the graphical representation of Boyle's law. So basically, as pressure increases, my volume goes up. So what we can see here is, as we go this way, right, we see that pressure is increasing. And as you go that way, you also see volume is getting smaller. Not a lot at that point, but starting initially, right? So when my pressure goes up, my volume goes down, or vice versa. If volume goes up here, like we're seeing going up, right? Then we can see when volume goes up, the pressure must be going down. So Boyle's law will always have this curvature nature of the graphical representation in lab. So if we looked at different gases and changed the pressure or the volumes, we're going to see this holds true no matter what. Again, at low pressures. All right, so let's look at the exercise number 3. So in this exercise, we're going to do a quick calculation on here. So it says sulfur dioxide, a gas that plays a central role in the formation of acid rain, is found in the exhaust of automobiles and power plants. We consider a 1.5 liter sample of gaseous SO2. So that's a volume because that's in liters, right? And that gaseous sample is at a pressure of 5.6 times 10 to the third pascals. So there's my pressure. And it says if the pressure is changed. So I have an initial set. So that's 1, or you can use initial, however you want to do it, of volume and temperature or pressure conditions. And then what we do is we change it. So now all of a sudden here's the new pressure. And we want to know, what's that new volume going to be, assuming constant temperature, and we would also assume that they would be keeping, in the scenario, keeping the moles of the gas or the quantity of gas constant. So Boyle's law, when I only have pressure and volume and I keep the temperature constant, is P1 V1 equals P2 V2. So all we're really doing with gas laws, which is nice, is algebra. And algebra is pretty simple, so we're just going to plug in what we have. So pressure 1, we have 5.6 times 10. I don't know why my pen's not working very good. Times 10 to the third pascals. And we're going to multiply that by my volume, which is 1.53 liters. And then that's going to equal the new pressure, or what it's changed to, which is 1.5 times 10 to the fourth. Again, having issues with my pen. Pascals. And we're looking for volume 2. So then we're just doing the algebra, dividing the 1.5. I'm not going to show you the algebra on all these problems, but I will show you on a couple of them just because I think it helps for you guys to see. Now, one thing that is important when you are doing this is everything has to be in the same units, because if it's not in the same units, the units won't cancel. So when they cancel out, we should be left with the volume unit, which is what we wanted here. So with sig figs, we always go with our fewest number. So my volume, the new volume, is going to end up being 0.57 liters with 2 sig figs. So that should make sense because we can easily see that our pressure went up, right? So we want to double check and make sure, does this fit with what we think should happen? So pressure went up, so therefore volume should have gone down because they're inversely related. Well, it did go down by a third, 2/3, probably about 2/3. All right, so Boyle's law is relating the pressure and volume, and it's one of our most used laws because a lot of times we are studying pressure-volume relationships with constant temperatures. Like in a classroom, we're not really changing the temperature very often kind of scenario.